What if I were Thomas for the summer? Western blot. So Western blot is used to quantify protein. And things to note is that the protein of interest must be soluble. In other words, it has to be hydrophilic. And if it isn't hydrophilic, we need to make them hydrophilic by using a solubilizer. To make them hydrophilic, such as urea or uric acid. And first of all, you need to get the sample. After that, you need to isolate your total protein from the sample. And how you do it is with isolate total protein. And how you do it is by homogenizing them with trisol. In other words, blend it up with trisol. And then you're gonna centrifuge it. And it's gonna make these layers where this pink is going to be protein at the bottom layer, and this is DNA, and the top layer is RNA, but not important items. So bottom layer and centrifuge it to get the protein. After that, we need to quantify the total protein. We have to figure out how much protein we have in this solution. And how we quantify this protein is through Bradford assay. Quantify P with Bradford assay. Bradford assay shows different colors with different concentration of protein in the solution. And we can use a BSA, bovine serum albumin, and we can make samples, different samples with different concentration. So like 0.5, 0.6, 0.7, 0.1, yada yada yada. And higher the concentration, the higher the protein concentration, higher the absorbance it will show on the spectrometer. And we can make this a nice curve, and we're gonna call it standard curve. Although, ironically, it's not curved, it's a linear line, linear curve. And one thing to note is that you cannot go beyond the range of the standard curve sample. So you cannot go beyond out here. You cannot interpolate the protein concentration outside of this value, as you cannot ensure the accuracy of it. And so once you make a standard curve with bovine serum albumin, you can now test your sample and interpolate the protein concentration on your samples. Once you have done it, you will get sample 1, let's say it have 140 microgram per microliter, sample 2, 302 microgram microliter, sample 3, 227 microgram per microliter. So we have this protein concentration. And in order to run the electrophoresis, is that right?
Electrophoresis, yeah.
Electrophoresis. We have to load on the well. We have to load the same amount of proteins on each well. And that means we can either, first thing is to, we can dilute all of them to the same amount, same concentration, same amount on each well, or we can calculate if you're trying to put a, let's say, 200 microgram per each well. Well, we have to put little. We'll have to put roughly 1.5 over here, 1.5 microliter over here for the sample 1, and then for sample 2, we have to put about 0.7 microliter over here. So we can use different concentration with different volume of solution to put the same amount of protein in each well. So the next step is called SDS page, which page stands for polyacrylamide gel electrophoresis. So once we have our protein ready, we have to actually heat them up. So let's call it prep, protein prep. You have to heat them up. So what it does is untangle the protein. So it was like this, and then now it's very much untangled. And then we have to coat them with SDS. And what it does is gives negative charge. So we're going to coat each protein with negative charging. And then we can put it to the gel, the mini well. So we're going to put S1, S2, S3, and then on the last one, we want to put molecular weight ladder. And what molecular weight ladder is a known, it's a concoction of a different substance with a known molecular weight. So we can see, so similar to like the PCR electrophoresis, smaller molecular weight is going to go down faster. So we'll have something like 50 kilodalton, and then 40, 45, that's a 40, 70, 100, and 140 kilodalton. And because we have this known molecular weight ladder, and it's worked kind of like as a ruler, so if you didn't have the molecular weight ladder, even if we got our result, we won't be able to tell which one has we won't be able to tell the molecular weight of each these proteins. But because we ran with molecular weight ladder that has a known molecular weight, we can compare with molecular weight with our result to tell what kind of molecular weight each proteins are. And they're all going to have they're going to have a lot similar if they were the same sample. One thing to note is that the SDS coating has a dye in it. So when we actually run our electrophoresis, it's going to show this kind of dye, and it's going to come down as time goes on, and it will eventually disappear. And that's when you should stop the electrophoresis. The dye is actually just a little smaller than your smallest protein, So it travels just a little faster than your smallest protein, and once it disappears, we know the smallest protein is kind of close to the bottom, and we don't want the protein to escape from this gel, and that's so once the dye is out, that's how we know when to stop electrophoresis. Once you have this gel electrophoresis done, we have to transfer them to the different membrane. And how we do it is by putting, this is called 4, 5. We have this copper plate that's a negative charge. We have this copper plate that has a positive charge. We're gonna sandwich. We're gonna make a nice, delicious sandwich. Let's put some nice ham in the center. That is this gel that has a protein in it. And then you can put this membrane. They call it Blot membrane. Well, works as like a filter. So protein cannot go through it, but other solutions can. And we're going to put some sponge that's wet, saturated with solutions that allows the electrons to move through. And the basic main thing is that, so this is membrane. So since protein is charged with a negative charge, it's going to try to go downward toward the positive end. But because it cannot go through this membrane, the protein will be transferred on to this nitrocellulose membrane. After this step, we will have this. So this is going to show this nice set of proteins. It's still, at this point, it's not visible to the bare eyes. So what we need to do is tag with antibody. Tag with antibody. We can first tag with our primary antibody. Primary antibody. And then this primary antibody needs to be tagged again with a pre-conjugated secondary antibody. They're usually pre-conjugated either with chemical luminescent or IR fluorescent bead. Fluorescent blot, IR version is more widely used. It is to be noted that beta-actin and GAPDH, they are two types of protein that are widely used as a reference protein. So we'll run some reference protein together. I'll mark them with like a blue. So if you have this reference protein, what it does is that we can we'll put a known concentration of this beta-actin and GAPDH into the electrophoresis. And because we have this known concentration, we can, once we take the picture of this result, we can calculate the intensity and match it with the concentration. So, and use that to kind of figure out the other concentration of the other proteins. So it's like a intensity calibration. And why we use Western blot is over other immunofluorescence is that it gives us more control over like detections, because we can set different kinds of concentration of protein that we are putting in, and like the amount of protein. We have control over how much protein we are putting in. So if it's a protein that's really hard to detect with immunofluorescence, then we can put a whole bunch of proteins into the well and wait for the, and they will have a thicker band, and it will be easier for us to detect. I'm not sure what I explained makes sense to anyone.